Hello world, my name is Zhang from National University of Singapore. Today I'm really glad to be here to introduce you one of our recent work entitled Securing Practical Quantum Cryptography with Optical Power Limiters. And here's the outline of this presentation. I will be introducing you how and why we need power limiters, and I will show you our experimental and simulation results. Also, for security reasons, we've considered some possible attacks to such power limiters. And finally, I will be introducing you one of the applications of such power limiters in a plug-and-play MDI-QKD system. Let me start by showing you a lot of practical attacks to a QKD system. QKD is secure theoretically, but considering practical implementations, we can always find a lot of loopholes on different components. Simply speaking, we can just characterize them based on the target, either receiver or source. And luckily, we have well-developed MDI-QKD, which could close the detector loophole. But for transmitter side, we still have to find a practical and secure way out. Power limiter, or energy bound, is one of the important tools. One main application is to solve the Trojan horse attack problem. In a typical QKD system, Alice encodes the information and sent to Bob for decoding. And an important assumption here is that the equipment for Alice and Bob should be placed in a secure zone, free from eavesdroppers. While it is not true with practical equipment. Eve could inject a strong light into Alice's equipment and collect the reflected photon with the encoded information. And this is dangerous and couldn't be detected by just looking at the error rate. So to solve this problem, there has been a few countermeasures proposed. Phase randomization could reduce the information collected by Eve by a small amount, or Alice can put a detector here to monitor any unauthorized strong light input. But active components like detectors can be damaged or even bypassed. So that is why passive components still catches people's eyes, like isolators. It has limited degree of freedom, thus has lower probability to open new loopholes. But for isolator, it is for one-way application only and requires high isolation in practical case. So no matter for which type, the basic idea is to limit amount of unauthorized input power. So that's where the power limiters come in. Another field requires energy bound is the semi-DI framework, including quantum key distribution or quantum random number generation. So semi-device independent here basically means the security of the scheme depends only on limited assumption, like here only on the mean energy. So as long as we can trust the energy bound, the QKD or QRNG will be secure. And here we can bound the overlap between state 0 and state 1 in a BPSK scheme by bounding the mean energy, which is basically the distance between those two states. So the certifiable inherent randomness comes from the minimal overlap here. Again, a power limiting device is very important here. So with the previous examples, we can define here what we need from an ideal optical fuse or power limiter. It has to be reliable and characterizable, and it would be great if it can provide a threshold of a few photon to hundreds of photon level. And by its name, it will just stop the communication channel once the input goes beyond the threshold. And it needs to be cost-effective, passive, and easy replaceable. And most importantly, it should be independent of other degrees of freedom, such as frequency or polarization, which is important so that it won't open extra loopholes. So with all the security proof with energy constraint, it is just the right time for us to develop such a device. There are a lot of previous work that could provide energy bound in an optical system. One could depend on the fiber damage threshold, including the damage to the connector, fiber itself, or the cladding. It could provide a limit about 10 to the power of 2 to 10 to the power of 3 milliwatts. And another type we can categorize it as the filter-based. As an example, here's the ring resonator from a photonic platform. We can use the Thermo-Optical effect or optical force to tune the filter center wavelengths when the input power is super high. So with this type of power limiter, the problem is the narrow operation bandwidth and limited extinction ratio. We can consider a typical 20 dB extinction ratio of such a device. The eavesdropper could simply just add another 20 dB to her input power. Then the device will be useless. So the third type we consider is the nonlinear effect. To photon absorption, the input power limit is around 10 to the 10 to the power 3 milliwatts level. And another effect we can explore is the Thermo-Optical defocusing. It has a relatively low threshold and a simple design. So our power limiter is mainly based on this effect. Here's our power limiter design. And we will have an input-output fiber as the optical interface. And we use a pair of collimators to collimate the light. And one thing to be noticed here is that we use a reflective collimator. So it will solve the dispersion problem comes with broadband operation. And an active medium with negative thermo-optical coefficient is put in the optical path here. So here we choose acrylic. And the input laser will heat up the center of the material, which will reduce the refractive index and makes the prism looks like a concave lens. And higher absorbed power will just diverge the input light more. Then, if we put diaphragm here, we can control the received power by just tuning the diaphragm width. And a filter could be introduced here to limit the input wavelengths to prevent wavelength attack. We will provide more detail on this later. So basically that's it. All we use is off-the-shelf components to provide a robust and cost-effective design. So here in this page, I'm showing you the theoretical model we have for such power limiter device. So in this equation shows the angular divergence of a paraxial light passing through a refractive index gradient like this. And this equation shows that basically the basic mechanism inside the material is the laser optical power is balanced with the heat transfer mechanism. So by solving all those equations, we are able to get the laser intensity at any position inside the material. So from this equation, we can see that this part contributes mainly to the absorption of the material. And this part will just give us an expanding Gaussian beam shape. So we also confirm this by COMSOL simulation. The COMSOL can tell us that here's the temperature distribution inside the material. We can see a very strong temperature gradient in the R direction of the material. And this will just cause the light beam to diverge inside the material like this. So with the theoretical model, we can calculate the input-output power relationship of such a device to confirm the power limiting effect. So in this figure, you could see at first the output will just increase with the input, and after a certain threshold, the output will start to decrease. And we notice here that the power will drop all the way down before the fiber diameter threshold, which is taken from this paper. So by changing the prism length, and we can shift the output maximum power downwards. And if we pick up the input-output value of all those peak points and plot them in this figure as a function of the length, we can see that the nonlinear limitation happens below around 10 centimeters. So above 10 centimeters, the response seems more or less linear, which means the material absorption starts to dominate. And also we perform the simulation on the effect of diaphragm width. So we can see by increasing the diaphragm width, the curve becomes more and more flat after the threshold power. So just basically we can just customize the input-output relationship by tuning these two parameters based on our requirements in the application. Another important consideration is the response time of such a device. We did simulation and experiment of the device under step input to confirm this. The result shows that the device has a very long response time of around 0.2 seconds. So the output will be limited eventually but there's a high peak at first. And this would just give us the impression that if we use a shorter pulse, we can just bypass the power limiter and provide a higher output. So we did further simulation to verify this. Here we consider a series of input pulses with same average power but with different duty cycle. So with the duty cycle increase, the peak power will just decrease to maintain the same average power. And this figure shows the maximum temperature inside the power limiter as a function of time. So when we increase the peak power, the temperature will just increase faster, and the power limiter could reach a higher temperature. As a result, so shorter pulse will actually experience a larger divergence and a greater power limiting effect. And the output average power is also plotted as a function of duty cycle. So it tells us the pulse input experience greater power limiting effect compared to the continuous wave case here. So in the security analysis follows, we can safely use average photon number as the worst case scenario without considering the waveform. In the next few slides, I'm going to talk a bit on the possible attacks. And first thing is the wavelength dependency of such a power limiter. Thermo-Optical coefficient is modeled by this equation, where n is the refractive index, and phi here is the electronic polarizability, and beta here is the volumetric expansion. And in most polymer, this is the dominant component. So the fundamental nature of TOC in a polymer is just the thermal expansion after absorb the input laser. So this doesn't really relate to the wavelength naturally. And as you can see from this table, the TOC of acrylic has been measured from about 400 nanometer to 1550 nanometer with almost the same result. So the only thing we have to consider here is the absorption spectrum. And this is taken from a material handbook and marked a few interesting points: 1550 wavelengths, 1310 wavelengths, and also the point where the absorption loss is at the minimum of around 0.15 dB per centimeter. And I can then calculate the output power bound as shown in this figure. So, and there is definitely a problem here. So the eavesdropper could just use the visible light for Trojan horse attack with a much higher bound than 1550 wavelengths. And of course, we can just use the worst case scenario as the final bound, but the easiest way is actually just filter the visible wavelengths, and this will also provide an extra protection for our QKD system. So here we choose just a box silicon absorber, and because its potential of high damage threshold, and considering a fiber damage threshold of around 12.8 watts, the output power spectrum will just become something like this. With silicon thickness shift from 100 micrometer to around 10 millimeter, the curve will just shift in this direction, and it will just provide us a worst case scenario in the communication wavelengths. Another attack we consider here is the laser damage attack. There has been a lot of research demonstrated that a strong laser could damage the protection components, including filters and attenuators. So here we also spend some time analyze how the material responds to a strong light. As shown in this table, acrylic has a melting point of around 404 K and a boiling point of about 473 K. And based on the simulation here, we can see that the material will be melted and evaporate with about 400 milliwatts of input power. So this is basically exactly the same as the laser cutting or laser drilling process, where they typically use a different wavelengths. So in order to protect other optical components, we can actually implement a reflection structure like this. So under extreme high power, the power limiter could just act as a fuse to the optical path and then protect all the optical components in behind. And finally, I will introduce you one of the applications for such a power limiter. plug-and-play MDI-QKD. The system looks something like this. Alice and Bob are the users with identical equipments, and Charlie here is the central server where expensive detectors and lasers are placed. And a common laser is placed here and sent to Alice and Bob at the same time. The users will just attenuate and modulate the input signal and send back to Charlie for the biostate detection. An advantage for such a plug-and-play MDI includes the robust performance with simple setup. And because the user doesn't have to purchase expensive laser and detectors, and also with a common laser source, the wavelengths could be identical and clock synchronization would be much easier. So, and also birefringes and polarization dependent loss can be suppressed. But the main issue limiting the application of such plug-and-play type is the Trojan horse attack. Because of this two-way structure, eavesdropper can always send a strong light and collect the reflective photon. The average photon could provide Eve with additional information about the encoded phase. So that is why we need a power limiter here to limit the amount of input power. So with the power limiter considered, we did a simulation on secured key rate. The black curve here shows the ideal case without Trojan horse attack. If we consider an average Trojan photon of about 10 to the power of -3 per pulse, and we are still able to bound the information leakage and provide a secure key rate in the red curve without much compromise on the total performance. One thing to be noticed here is that we assume the Trojan horse attack from coherent state only. So it doesn't matter whether we use CW or pulse as long as it's a coherent state. So the result here is more like an optimistic upper bound to show the potential of this device. The full security proof is ongoing in our group, and the proof technique is taken here if you are interested. Okay, here's the conclusion for this presentation. We already provide an ideal model in the beginning of this presentation to show like what a power limiter or optical fuse should look like. And here's what we can achieve. So for our scheme, we can have a passive power limiter at milliwatts level. And we can always use additional attenuation to achieve like full photon level limitation. And also if the input energy exceeds the threshold, the output power will be limited and start to decrease. And we have a cost-effective, passive, and easy replaceable design. And importantly, the power limiting effect can be achieved for both CW and pulse light. And also it is wavelength and polarization independent. So what we need to do in the future is like we need to provide a full secure analysis of MDI-QKD with untrusted light source. And also we can collaborate with others to provide a measurement on visible wavelengths and high power lasers. I would like to thank everyone in our group for their contribution and support in this paper. And also we are opening for postdoc positions. That's all for my presentation today. Thank you very much.